Hello everyone and welcome back to the channel. Now for those of you who know that I'm living in Chicago, you might also put two and two together and realize that it is the DNC week over here, meaning that we have quite a few protesters. Now some of you may tell me to stay safe, but the reality of the situation is I'm actually out there protesting with them. Because it has been far too long that Taco Bell has not had anything on the value menu for $1, and that is not going to stand. So I do plead whoever the next president is to please make them reconsider that, but until then I'm just going to have to keep making these systems design videos. Alrighty, so today we're going to be covering Bigtable. So Bigtable is another paper out of Google. Now you might think, oh Jordan, you're just glazing Google this whole time and only doing papers by them. Well, that's not true. Trying to go in like a general chronological order starting in the 2000s here, and they did put out a lot of important stuff. Eventually we'll move away from Google, but they've got some useful papers. So this paper was released in 2006, although they say in it they were basically designing Bigtable for multiple years beforehand, even so far as the late 90s. So basically it is a database for semi-structured data. So you do define a schema, but you don't necessarily have to fill out all of the fields, and it is going to be built on top of a bunch of existing Google tools that we've already covered, such as Chubby and GFS. So Chubby, if you recall, is used for basically building a distributed course lock. GFS is of course going to be a distributed file system. And so basically Bigtable is going to be the main inspiration for some open source software, in particular HBase. And similar to how GFS is built, or rather Bigtable is built on top of GFS, HBase is built on top of Hadoop and more specifically HDFS. Cool, so the first thing that we're going to do is start by explaining that whole semi-structured piece. What is the data model of Bigtable? So basically, in Bigtable, all of our data is going to be sorted or indexed by one row key. So that's going to be on a per table basis. And so basically within one row, you can have these single level transactions. They don't support multi-level transactions because it would add a lot of complexity to their system, and they find that most of their users don't end up using them. Number two is that unlike some systems that we've seen where data is actually going to be partitioned by basically the hash of this row key, in Bigtable we are actually partitioning everything by just the pure row key range. The reason they do this is to make it a little bit easier to do something like a range query, which they do actually find that they use pretty often. However, one problem that we do often notice when we have something like range-based partitioning is that we can have hot partitions because not all ranges are necessarily equal. And so what they'll do is also allow you to do dynamic partitioning, where basically as particular row ranges get more saturated or more load on them, we can actually go ahead and split those up and even merge them back together if they are not very popular. Another thing to note is that each row can have something called column families. So this is something that is unique to Bigtable and HBase. I haven't actually seen this used elsewhere. But the gist is basically you can have a column family where, for example, you might define one called books, right? If we have some sort of like table where we have an author and their books. And so the gist with a column family is that even if I have this family, I can have multiple column keys within a column family. So let's say a column key itself might be a book name, and then you also want to express some sort of metadata about the book, such as like when it actually came out, maybe, kind of the length of it, other metadata about it, like where it would be stored in a library, stuff like that. So that would be the book data. And the gist is that within a column family, all of the data should be of the same type. We'll talk about the reason for this later, but hint, hint, compression. And number three is that we also have some sort of timestamp on all of these pieces of data to basically ensure that we can have many versions of the same data. This is going to allow us to do lookbacks or things like snapshotting or anything like that. And so you can either supply those timestamps yourself or you can have Bigtable calculate them for you. Cool. So just to give a more concrete data model example, we discussed this momentarily ago, but we might have an author over here, and then we have the books column family. So kind of a convoluted example on my part, but the point is your column key would be the book name, and then you would have some metadata over here as the actual data in the column family. And so for example, like I mentioned, we are doing our partitioning by row range, so maybe this is one partition over here, the other one is another partition, and again, we're using range-based partitioning. Note how the D is next to itself, and then the J's are also next to one another. And so each of these partitions, the term that Bigtable uses is called a tablet, and we'll discuss what this means a little bit more in a bit. Cool, so let's talk about some actual building blocks of making our system here. So I've spoken about LSM trees and SS tables plenty on this channel before, and I don't really want to go into them too much again, but the gist is that SS tables are basically sorted, immutable files that we use to basically store our database data, right? So for example, if we have a bunch of keys and values, you might have A is equal to 10, B is equal to 5, C is equal to 7, D is equal to 8. And so these are just going to be ordered on some table on disk. And so what Bigtable will do internally is actually break these into all of these 64 kilobyte blocks. And then the reason that they do that is because now we can establish some sort of thing called a block index. So a block index would look something like this. We would store it in memory, and then you would maybe say the first entry or the first key at each index, so that if I'm searching for a specific key, I can quickly binary search my block index, and then I know which block of the SS table I have to go ahead and read to find the key that I care about. So we're going to store SS tables in GFS. We're also going to store our write-ahead logs in GFS. Now you might be thinking to yourself, why do we need a write-ahead log in the first place? Well, when we write new data, it actually first gets buffered in memory before it gets sank to GFS, and as a result of that, we basically need to have some sort of write-ahead log to ensure persistence of all of our data. And then we also use Chubby a lot. So I've spoken about Chubby in its own video, but this is really useful for things like avoiding duplicate masters, doing service discovery, and also just seeding out our startup information. Okay, so that's all pretty abstract so far. We're going to continue to dive into this thing more and more concretely throughout the video. So basically, Bigtable is made out of two components. One is going to be tablet servers. So these are responsible for serving those tablets, or the row ranges of a specific table. And so basically each of these tablet servers might be holding anywhere from 10 to 1,000 tablets. And of course, if a tablet server deems that one of the tablets that it's holding onto is too large, it can actually initiate a tablet split process that we'll talk about later in the video. Additionally, we also have the master server. So note how this is a pretty similar design to some of the other Google patterns that we've seen, such as MapReduce and also GFS, where there's a master server and then a bunch of these kind of inferior servers that the master is controlling. So basically, the master server is responsible for tablet assigning, right? We have a bunch of these tablet servers. They need to be assigned a bunch of tablets. The master is the one with the global state that can do that. And so additionally, in order to avoid our master server becoming a bottleneck, it's great if our clients can avoid having to reach out to it directly in order to make reads and writes to tablets. And so that is another thing that we try and keep in mind. So the question becomes, well, how do they actually go ahead and find a tablet server if they aren't speaking to the master? Now, this is obviously going to be a legit problem. So what we do in GFS is we have something known as the metadata table. So the metadata table is basically recording the locations of every single tablet and which tablet server that it lives on. So, for example, if I have, a couple of Bigtable tables, so Jordan's Ladies and Jordan's Enemies, I can see that in Jordan's Ladies there are 3 tablets, and I can see in Jordan's Enemies there are 2 tablets, and then the metadata table, I can read it, and it's going to go ahead and tell me which tablet server these tablets are located on. Note that the metadata table also is going to tell me things like which SS tables are contained in each tablet, and that's going to be useful for the tablet servers to actually know what to read from GFS. So the question now is, well, we have this metadata table. The metadata table itself is a table in Bigtable, which means that now we have the meta problem of how do we know where the metadata tablets live? Because the metadata table itself might be so big that we have to split it into multiple different partitions or multiple different tablets, and as a result, if I'm a client, I need to know which metadata tablet I'm actually trying to read. Well, now we bring in something called the root tablet. So the one unique thing about the root tablet is that this guy is unsplittable. This does technically limit how many tablets in total we can have in our Bigtable cluster, but that's okay because in practice it's quite a few. So if I'm a client, basically the first thing that I'm going to do is when I start up, I want to go ahead and look at Chubby, because Chubby is going to give me the location of the root tablet server, or rather the root tablet. It's going to tell me the tablet server which I can reach out to go ahead and figure out where the root lives. So again, the root is living over here on some sort of tablet server. And then once I read the root tablet, from the client in step 3 over here. Now I actually know which tablet servers all of the metadata tablets live on, and as a result, I can read a bunch of the metadata and figure out where all of my subsequent tablets live, right? So I can go ahead and now all of a sudden reaching out to the actual user tablet servers that I care about. And so through this kind of tree-like process, we can really easily bootstrap a client with not too many reads and figure things out. Now you might say to yourself, it seems like kind of a slow process to have to go ahead and read this metadata every single time that we want to make a read or write. And you'd be correct. So actually the client will tend to cache a lot of this metadata. And so, if some of the requests begin failing because perhaps a tablet got moved to a different server, then they'll go back to the metadata table and they can start trying to read data again. And if, of course, a metadata tablet that they thought existed is missing, then they'd have to go back to the root and start reading it from there again. So ideally, not too many reads, but it is quite possible that this thing can get expensive. Cool, so let's now go ahead and talk about Bigtable startup itself, because we discussed what a client might do to bootstrap itself, but what do the actual Bigtable master and tablet servers do on their startup? Well, when a tablet server starts up, basically the first thing it needs to do is register itself in Chubby. And so it can do that pretty easily by grabbing a specific lock for its own server name. So maybe, if I'm server A, I go grab, /servers/A or something like that. And that way, the master can actually go ahead and quickly figure out what tablet servers are alive and going to be a part of its cluster. So now, what about the master process? What happens when that starts up? Well, the first thing that it does is it grabs some sort of master lock, and this is really useful to avoid something like a split brain. Number 2 is that it goes ahead and reads Chubby to see which tablet servers are alive. You could do that by basically just doing ls on the /servers directory and seeing which locks are grabbed. The next thing that it starts doing is sending heartbeats back and forth with all of the tablet servers. The reason that we do this is because ultimately the tablet servers are the source of truth for which tablets they hold, or which tablets they think they're responsible for. And so when the master does that, it can see which tablets are actually assigned and which ones are not. The reason it can see which ones are not is because it can basically go ahead and check, first off, if the root tablet exists and is assigned. The root tablet certainly exists, but the question is it assigned to a tablet server? If not, assign it. From there, the master will read the root tablet to basically learn about all the metadata tablets, and then it'll find all the metadata tablets, check if they're assigned to a tablet server, and if not, again, assign them. And then finally, by reading all of the metadata tablets from their corresponding tablet servers, the master can then see all of the existing user tablets, and then as a result, it can compare that with what it's hearing from the tablet servers and see if there are any user tablets that have not yet been assigned, and if so, assign them. So maybe a little bit slower of a process on the master startup, but it is still completely doable in not too much time. Cool. The next thing I want to talk about are network partitions, because this is basically what's going to happen if a master or a tablet server goes down. So like I mentioned, the master is heartbeating those tablet servers very frequently to get an idea of their state. Great. So what if a master stops hearing from a tablet server? I guess a few things are possible. For one, the master might be offline, and or it might just have some network partition that stops it from communicating with anything else. So the first thing that we're going to do if we're the master is we're going to go over to Chubby and try and grab and delete that tablet server's Chubby lock. The reason for that is that if we can do that, one, it means that that tablet server is actually down. It's not an issue on the master. And two, it means that we can now prevent ourselves from having that tablet server start back up without us knowing about it, right? So the master doesn't have to approve it or anything like that. Once we remove this lock, it basically says, hey, if the tablet server now is unable to grab this lock in the future, it can't rejoin our Bigtable cluster. Cool. So this is going to remove the tablet server from the cluster and stop it from coming back, like I said. And then again, the tablet server, once it notices that it can't grab that lock anymore, is just going to shut itself down. And then as far as the tablets are on that tablet server, right, because we had a tablet server, it had some tablets assigned to it, and it went down. Now, all of a sudden, those are considered unassigned by the master. So the master is going to have to go ahead and assign them again and make a bunch of writes to the metadata table in order to explain that. Cool. And then from there, basically, if the tablet server itself goes down on its own, even before it stops heart beating with the master. Ideally, it's got some sort of shutdown hook where it can release its chubby lock. That way the master is going to be aware sooner that it did go down. If it doesn't, eventually the master will basically stop hearing from that tablet server anyway, and the above process is going to happen. Otherwise, yeah, basically that lock is eventually going to be released automatically by the tablet server, because the chubby session with that tablet server that we discussed in our chubby video 2 videos ago is going to go ahead and expire, and then that lock is going to be released. Cool. So if our master cannot communicate with chubby, because for some reason it's having its own network partitioning issues, it's going to go ahead and kill itself. Even in the meantime, even if the master is shut down, keep in mind that just means that we're not assigning any new tablets, but all existing assigned tablets can still be read from and written to. And so it doesn't actually completely stop our Bigtable cluster if the master goes down. And then in a slight amount of time, we can basically spin up a new process that's going to go ahead and go back to chubby, claim that master lock, and start up all over again. Cool. So hopefully that's some high-level information on how we actually start up and get into a proper state in order to run and make reads and writes. But let's now go ahead and talk about actually making writes. So the way that Bigtable actually works is it uses that kind of SS table and LSM tree setup, where basically the LSM tree is itself in memory, and that's going to be some sort of like balanced binary search tree, and we call that in Bigtable the mem table. Maybe it's not exactly an LSM tree, but it is probably pretty similar in terms of its properties. And so basically the gist is when this guy gets too big, the LSM tree, we flush it to an SS table. Cool. So if we buffer writes in memory, like you can see we're doing right here, we have this mem table tree, and a write comes in from my client. The first thing that needs to happen is it needs to be put over here in some persistent commit log. Now it's not enough to just persist this commit log on the actual tablet server itself, right? Because if we just persist it there and the tablet server goes down, then we lost everything. So what we actually need to do is ensure that this guy is replicated over in GFS before we actually put our write in the mem table. So if you recall, that is actually a fairly expensive process because it means it has to be sent to 3 replicas and committed on each of them. So we discussed the GFS process of writing quite a bit more in the GFS video that I made a couple weeks ago, but the gist is you're basically pipelining the write down through the replicas for that particular commit log, or rather the chunks of the commit log. You're probably using an atomic append operation here, but again, probably a little too into the weeds for this video. And then eventually some primary GFS chunk server is going to commit that write. And once it's done, then our tablet server is going to hear back, and then the write can finally go up here into the mem table. Great. So that's a little bit slow, so we're going to talk about how we can optimize that in a little bit. Cool. So like I mentioned, when the mem table gets to a certain size, we want to flush it. So flushing the mem table has 2 purposes. For starters, it's going to free up memory on our tablet server, right? If we just let this tree over here get as big as possible in size, it's just going to get too big at some point, and then we're going to run out of memory and we're going to crash. Another thing that it does is actually act as a checkpoint in the commit log. So the reason that we have something like a write-ahead log or a commit log is so that if our server goes down, we can replay that write-ahead log. However, if we have to replay too many entries, that type of thing is going to be slow. So when we flush our SS table, or when we flush our mem table over to disk, what it actually does is create another SS table. So for example, this guy over here actually becomes this guy. And so maybe this mem table in particular corresponds to, say, 10 commit log operations. However, once we convert that to an SS table, we no longer have to replay any commit log operations in order to restore our state. Because these SS table files are all persisted in GFS, we've basically taken a checkpoint on our write-ahead log, and so now we can basically say, oh, if another tablet server comes up and has to take over this tablet, we have nothing to replay. It basically can just reference those SS tables in GFS, and we're good to go. Okay, now let's talk about something called major compactions. So minor compactions was the conversion of the LSM tree to the SS table and then replicating it in GFS. The major compaction is the fact that we might have many SS tables, right? Because every single time this guy gets flushed, it gets translated to an SS table over here. But eventually what we can do is actually compact those SS tables because the SS table files are immutable. And so when I make writes or I flush an SS table, it might actually be overwriting some data that was stored in an old SS table. So we can actually merge them together. So what does that look like? Well, basically we can do this in the background, but basically you take all the keys in common. Let's say this is the new SS table, this one is the old one, and then basically all the key value pairs in the new table have precedence over the old one. So you might see tombstones in a new SS table, but you won't see them in the merged copy as well. So basically the merge of these two is we know A is equal to 4, B is equal to 1 because that only appears in the old table, C appears in both the old table and the new table, but because the new table takes precedence, we know that 7 is the proper value, meaning that someone updated the value for C. The key G gets deleted, so we no longer see it in our new SS table that's been merged, and then F finally is equal to 12 because that's in the new SS table. So this is going to help us free up a bunch of disk space in GFS, especially when we have a lot of updates on our data that's already in SS tables. Cool. Let's quickly go over a couple of write optimizations that we can do in Bigtable because, like I mentioned, all of these writes to GFS are going to slow us down. So basically, the first thing to note is that the reason things are slow is because in a normal LSM tree and SS table index, you're basically writing straight into memory. However, because of this optimization, or rather this requirement that our commit log needs to be persisted to GFS, every single time we write into the mem table, we also have to basically make a GFS write, and that means that we're really basically synchronously replicating it to 3 different nodes. And so that is going to be expensive. So the idea here that we can actually do to kind of amortize our write cost here is the fact that every single tablet server, sorry about that, is going to hold many different tablets, right? Like 10 to 1,000 of them. And so we have many writes coming to that tablet server at the same time. So what we can do is instead of having one single commit log for every single tablet, which is probably the simplest way to think about the problem, what we can do is actually share them and basically have one shared log for all of the tablets on that tablet server. Then that way, for every single write into that commit log, maybe we can buffer them a little bit and then ultimately make that write at the same time so that way we basically write to GFS in batch for all of these tablets at once. This is what's known as a group commit, and it's not like it's going to improve the latency of every single write into our system. However, it is going to improve the throughput because now rather than having the overhead of all these small little network calls and all the replications that come with that, we're basically just doing one write to GFS for possibly 100 Bigtable writes, and that could be a lot better. However, the problem with this is that now we have one shared write-ahead log or one shared commit log for many tablets at a time, and that is going to make life harder for us. So if we have to restart one tablet in particular, for whatever reason, on our tablet server, now we have to basically parse through all of the entries on this shared commit log, and that can be expensive if there are a lot of entries. So what does Bigtable do to actually optimize for this? So let's say we have this tablet server over here. It's got A, B, and C on it, so 3 tablets, and then it goes down. And its commit log, keep in mind, this is persisted to GFS synchronously, so we know it's going to be in there and completely up to date. Looks like this. So we've got maybe one write for B, then another write for A after that, then another write for B, then another write for C, then another write for C, and A. And notice how they're all interleaved, because like I mentioned, we share a commit log for all of these tablets now. Basically, it would be a real pain if, these are 3 different tablet servers over here, and each one of them is taking on one tablet, and they all had to read this large shared commit log and only parse out the entries that they actually care about. Instead, what we do in Bigtable is basically we have our master. It wants to reassign all of these tablets. It knows the commit log corresponding to the tablet server that went down. So what it'll actually do is coordinate this distributed sort, right? So rather than looking like this, let's say this operation is called B prime, this is B double prime, this is A prime, this is A double prime, this is C prime, and this is C double prime. The master will basically be able to have this guy sorted up. And so eventually, we'll basically effectively run something like a MapReduce job. And then, we'll be able to send A prime and A double prime to this guy. We'll be able to send B prime and B double prime just to this guy, and then C prime and C double prime just to this guy. So the startup cost is a lot lower. We just have to do one big sort, and then we can go ahead and shuffle the relevant data over to the relevant tablet servers so that they can basically pick up that new tablet a lot faster. Okay, so we covered writes. How do reads in Bigtable work? Like I mentioned, the tablet server holds two things. One is going to be the mem table. We discussed that plenty in our write section. Number two are these block indices of every single SS table. So when I'm a tablet server and I get assigned some sort of tablet, I basically read from GFS all of these block indices. And like I covered way long back ago, this is basically almost like a table of contents for every single SS table so that we can quickly figure out in memory which specific block of the SS table that we want to look at for a specific key. So again, that's what we're looking at right here, block indices in memory. And that's going to allow us to not have to read a whole SS table file, but quickly figure out only the piece of it that we need to read from GFS. So basically on our read, the first thing that we do is go and check the mem table, because this is for all the recent writes, to see if it contains our value. And if it does, we return it. If it doesn't, then what we're going to do is go ahead and use all of our block indices to find the small 64 kilobyte block of every single SS table that would contain our key. And then now we know, okay, for SS table 2, maybe I have to read block 3, or that's where my key would be if it's in SS table 1, sorry. For this guy, maybe it would be in block 5. For this guy, maybe it's in block 12. And we're all looking for, key equals Jordan. And that's where the block indices tell us to look. So now all of a sudden we have to make 3 reads over to GFS, get those blocks, and then check if key equals Jordan is in there. Cool. So again, remember, reads from GFS are not trivially inexpensive because of the fact that these guys are likely on other servers, and as a result, we're reading over the network. We're not just reading from local disk, most likely. So the question is, if we're doing all of these GFS reads over the network and we're transferring a fairly significant amount of data, right? 64 kilobytes is not nothing, and we have to pull a block from each SS table at minimum, then what can we actually do to improve this? Well, one thing that we often see with these SS table type systems is using Bloom filters. So basically, to allow us to avoid making a GFS read for a given SS table, basically we can keep a Bloom filter in memory on every single tablet server. So this would be 1 per SS table. Or rather, you can establish one or pull in a Bloom filter as well when you're actually pulling in the block index for that specific SS table. And so what this is going to allow us to do is, the point of a Bloom filter is it's a small in-memory data structure that allows us to tell if a given key is not present in a specific SS table. It might tell us that the given key may be present in the SS table, and then we have to make that read, but it can potentially save us a lot of time by basically saying conclusively, okay, I know key equals Jordan is not in SS table 3, you can skip reading that one, and that's going to save us a lot of time. Another option that we can actually do is go ahead and cache SS table data on our tablet server. The reason we can do this relatively easily is because SS table files are immutable. And because they're immutable, that means we don't really have to worry about any cache consistency or anything like that. So basically we have 2 types of caching on the tablet server. Number 1 is going to be the scan cache. So the scan cache is basically going to store all of the merged SS table results. So let's say that, I want to look for the result of what is key equal Jordan equal to. I may have to check this SS table, and this SS table, and ultimately kind of merge those results together to get the proper answer. That being said, that's really only going to be good when we're doing repeated reads on the same exact key because it's this, final result. On the other hand, there's also a block cache, where a block cache is saying, ooh, you know what, I had to go ahead and go to GFS and read this specific block of this SS table over here. It would be great if I kept this around in case we do a sequential read off of the data that we just accessed from that SS table. And so again, the block cache is good for sequential reads, the scan cache is good for repeated reads. And so the final piece of what I want to cover basically for this video is how do we actually store data in these SS tables themselves? Because so far I've been a little bit vague about that. So to understand this, something that is very central to Bigtable is called locality groups. Same deal in HBase. So basically, we've spoken about column-oriented storage plenty on this channel, but Bigtable uses it. And the way that you basically specify which columns you want to store together are via something known as locality groups. And the nice thing about these are they're user specified. So Bigtable doesn't have to do any coding or any figuring out what it should store locally together on disk. The user basically says, hey, I've got a few columns. I know I'm always going to be accessing these together. Put them in the same locality group. They'll go in the same SS tables. And then we can use different SS tables for different locality groups. And that allows me to make more granular reads when I do go to GFS. So this is another nice read optimization. Another thing that you can actually do is you can use compression. Because like I mentioned, within the same column family, data should be of the same type. And as a result, GFS, or rather Bigtable, allows you to run plenty of different compression methods, and they've been able to achieve really nice compression ratios. They've been looking at something like almost 10-to-1 for some of their tables. Cool. And the last piece of functionality that Bigtable allows with locality groups is you can actually serve the data not just from SS tables, but also from memory. So the way that they would do this is they do originally still get written to SS tables in order to be persistent. But then if you're a tablet server, right, I'm this guy over here, TS, and I read from GFS, and GFS returns me an SS table, and I see maybe in my metadata, oh, wait a second, this locality group belongs in memory, then I can basically cache that whole file. And so this is really nice too, because certain columns you want to be particularly fast to read from, and this is going to allow us to do that. Of course, it means that you probably don't want to store as much data in these column families, but that is a trade-off for the user to ultimately make. Cool. The last piece of the puzzle here is going to be tablet splitting. So I mentioned basically that if a tablet server deems, hey, one of the row ranges that I'm holding or one of the tablets that I'm holding has gotten either too big or there's too many requests on it, it may opt to ultimately split that thing up so that a different tablet server can take the other half of that new tablet. So basically this is done in a few different steps. If I'm a tablet server, the first thing that I'm going to do is go ahead and write to the metadata table and say, hey, wait a second, there's actually a new tablet in town, and here's what it is. Cool. Now, the second that this thing is written into the metadata table, we know that all writes to Bigtable are effectively instantly persisted, right? Because they go into GFS, and the same applies for the metadata table. So now we have this thing committed. We're basically good to go. If our master goes down at this point, if our tablet server goes down at this point, that's fine. All we need to do is read the metadata table and see that this tablet has been split, and then we can figure things out from there. But the gist is, now all we're going to do is take our new split tablets on our tablet server, and they can both use the same exact SS tables as the parent tablet. This is a nice optimization because it means that we don't have to read in existing SS tables and split them into two pieces for both tablets. The reason they can both use the same set of SS tables is because the SS tables for the parent tablet contains all of the data that could possibly be asked for in the split tablets, so it's totally fine to basically just both reference that same set of SS tables. We could potentially clean this up later via something like a major compaction, but for now this is going to allow us to make this splitting process really, really quick. The next thing that we're going to do is we can actually go ahead and perform a minor compaction on the tablet that we're about to split. So the reason that we want to do a minor compaction is that this basically clears out the commit log, in the sense that we know, since all of the data will be flushed to SS tables, that we can actually go ahead and just point to the SS tables for the tablet when we load it onto a different tablet server, as opposed to having to replay a bunch of entries in the commit log. Because like I mentioned, when you do a minor compaction, that is effectively taking a checkpoint of the commit log. So it clears out that mem table, it takes a checkpoint of the commit log, and basically says, as long as you know about all these SS tables, you're good to go. At this point, our tablet server that's doing the splitting is going to stop serving one of the split tablets. It's going to be heartbeating with the master, who now sees that there's an extra tablet that is not yet assigned anywhere. And then the master is going to go ahead and reassign it. And now the other tablet has the new split assigned. So, right, if we had this tablet before, maybe we went ahead and split it in two. This guy might stay where it was. And then this guy goes to some other tablet server. And then the other tablet server knows that, let's say this whole thing was referencing these two SS tables before in GFS. The other tablet server is still going to be referencing those same exact tables in GFS because they both contain all of the data. So just like that, we can actually split our tablets out really quickly, which is good because it means that in theory we can balance our load fairly evenly. Okay, just a quick shout out to a couple of other optimizations that we do see in Bigtable. One of them is just doing garbage collection in the background. Because we have all of these compactions and because all of these compactions are on immutable files, if two SS tables get majorly compacted or something like that into a new SS table, the old ones are going to stick around in the background. So the master can periodically see, hey, I see a bunch of SS tables that are not being used anywhere in Bigtable. I can go ahead and tell GFS to clean those up. Cool. Number 2 is going to be concurrency in our mem table. We want to be able to make writes as quickly as possible, but at the same time, ultimately, it's really, really nice when we don't have contention on reads on our tablet servers. So in order to avoid read contention, which would basically mean grabbing a lock somewhere on our mem table, we use copy on write semantics, which basically means don't grab a lock, take the row, copy the data, basically read it first, copy the data, make your modification, change the pointer. So that's going to be a lot easier. And of course, as far as actually reading SS tables go, when we're doing reads, we don't have to do any locking on those because they're completely immutable, so we don't have to worry about contention in the first place. Cool. A couple of performance observations, since they do spend a fair bit of time in the paper talking about this. Basically, one, the main thing that you do care about when you're building out a massively distributed table like this is that performance increases with more tablet servers. Now, unfortunately, as nice as this would be, because in theory it should increase at a linear rate relative to the number of tablet servers, it does not. The reason being that basically the Bigtable design throttles how frequently tablets will split up, or tablet servers will split up tablets, so that they don't, overload the system with constantly rebalancing. Number 2 is fairly weak performance on random reads. Like I mentioned, SS tables are split into blocks. Those blocks are fairly large at 64 kilobytes. Let's say you only wanted to read a few different bytes of data. And so if you only want to read 10 bytes of data, you don't really need to load in all 64 kilobytes. And so that is going to be a lot of overhead there. So for Bigtable applications where you're making a lot of random reads, sometimes it makes a little bit more sense to lower this number from 64 kilobytes over to 8 bytes. The last piece of it is just you can get really, really good compression with column-oriented storage. They were getting things like 6-to-1 or 10-to-1 compression in some of their column families, which I think is very impressive. Cool. As far as conclusions or my own takeaways for this video, I think number 1 is that as much temptation as there may be to make this kind of one-size-fits-all type of system where users don't really have to configure everything's abstracted away from them, and we store data in the best possible way, the Bigtable founders concluded more or less that sometimes it's better if the users can make this specification because it's just a lot less work to maintain something like that, and it's a lot less opaque, which is really, really nice. Number 2 is the usefulness of Chubby and coordination services in general, because even though Chubby is not Zookeeper, it's quite similar, and so you can see how, great for service discovery, great for avoiding split brand. Don't try and re-implement this yourself. If you have an existing service that does these things for you, it is going to make your life a lot easier. Just make sure to use it as intended, right? This is for coarse-grained locking. It's not for fine-grained locking, and so be careful with that. And last but not least is, of course, like all of the systems that we've covered so far, plan for failure. When you're running many nodes, hardware failures are more of an inevitability than anything, and as a result, you want to build out quick recovery mechanisms. Even though the master itself might not fail very often, right, because there is just one master, so the chance of failing it is low, we can survive a master failure. It doesn't bring down everything. It may take a little bit to start up a new master, but that's okay. And more importantly, in the more common scenario, if tablet servers go down, we have a very, very optimized recovery process. We have these write-ahead logs that exist in GFS. We can go ahead and pull them quickly. We do this distributed sort on the write-ahead log, and then we can go ahead and split up all those tablets on the tablet server and just distribute them out to a bunch of other tablet servers. Anyways, guys, I hope that you found this video interesting. I'm going to sign off for the week, but I will see you in the next one.